methods. With anode positive, with respect to cathode, a thyristor can be turned on by any one of the following techniques. These techniques are forward voltage triggering, gate triggering, dV by dt triggering, temperature or thermal triggering, and light triggering. The first method is forward voltage triggering. In this method, a forward voltage is applied between anode and cathode with gate circuit open. Junction J2 is reverse biased. As a result, depletion layer is formed across junction J2. The width of this layer decreases with an increase in anode cathode voltage. If forward voltage across anode cathode is gradually increased, a stage comes when the depletion layer across junction J2 vanishes. At this moment, reverse bias junction J2 is said to have avalanche breakdown, and the voltage at which this occurs is called forward breakover voltage, and it is denoted by VBO. The name forward breakover voltage is given because at this voltage VBO, current voltage characteristics breaks over and shift to its own state position with breakover current IBO. At this voltage, thyristor changes from off state, that is high voltage with low leakage current, to on state characterized by low voltage across thyristor with large forward current. As other junction J1, J3 are already forward biased, breakdown of junction J2 allows free movement of carriers across three junctions, and as a result, large forward anode current flows. This forward current is limited by the load impedance. In practice, the transmission from off state to on state obtained by exceeding VBO is never employed as it may destroy the device. The magnitude of forward breakover and reverse breakdown voltage are nearly the same and both are temperature dependent. In practice, it is found that VBR is slightly more than VBO. Therefore, forward breakover voltage is taken as final voltage rating of the device during the design of SCR application. After the avalanche breakdown, junction J2 loses its reverse blocking capability. Therefore, if the anode voltage is reduced below VBO, SCR will continue conduction of the current. The SCR can now be turned off by reducing the anode current below a certain value called holding current. The next method is gate triggering method. In this method, the forward voltage at which the device switches to on state depends upon the magnitude of gate current. Higher the gate current, lower is the forward breakover voltage. When positive gate current is applied, gate P layer is flooded with electrons from the cathode. This is because cathode N layer is heavily doped or compared to gate P layer. As the thyristor is forward biased, some of the electrons reach junction J2. As a result, width of depletion layer near junction J2 is reduced. This causes the junction J2 to break down at an applied voltage lower than the forward breakover voltage VBO. If magnitude of gate current is increased, more electrons would reach junction J2. As a consequence, thyristor would get turned on at a much lower forward applied voltage. For gate current Ig is equal to 0 as shown in this figure, forward breakover voltage is VBO. For gate current Ig1, forward breakover or turn on voltage is V1, which is less than VBO. For Ig2 greater than Ig1, forward breakover voltage is further reduced to V2 less than V1. For Ig3 greater than Ig2, the forward breakover voltage is V3 less than V2. The effect of gate current on the forward breakover voltage of a thyristor can also be illustrated by means of a curve as shown in this figure. For Ig less than OA, forward breakover voltage remains almost constant at VBO. For gate current Ig1, Ig2 and Ig3, the magnitude of forward breakover voltages are OX is equal to V1, OY is equal to V2 and OZ is equal to V3 respectively. In practice, the magnitude of gate current is more than the minimum gate current required to turn on the SCR. Typical gate current magnitude are of the order of 20 to 200 milliampere. The next method is dV by dt triggering. So, in this method, with forward voltage across the anode and cathode of thyristor, the two outer junctions J1, J3 are forward biased, but inner junction J2 is reverse biased. This reverse biased junction J2 has the characteristics of a capacitor due to charges existing across the junction. In other words, space charges exist in the depletion region near junction J2 and therefore junction J2 behaves like a capacitance. If forward voltage is suddenly applied, a charging current through junction capacitance Cj may turn on the SCR. Almost the entire suddenly applied forward voltage Va appears across junction J2. The charging current Ic is therefore given by Ic is equal to dq by dt is equal to d Cj into Va by dt is equal to Cj d Va by dt plus Va d Cj by dt. As the junction capacitance is almost constant, so dJ by dt is 0 and current Ic can be represented as Ic is equal to Cj dVa by dt. Therefore, if rate of forward voltage dVa by dt is high, the charging current Ic would be more. This charging current plays the role of gate current and turn on the SCR even though gate signal is 0. Note that even if Va is small, it is the rate of change of Va that plays the role of turning on the device. The next method is triggering of thyristor is temperature triggering or thermal triggering. So, in this method, during forward blocking, most of the applied voltage appears across reversed bias junction J2. This voltage across J2 associated with leakage current would rise the temperature of this junction. With increase in temperature, width of depletion layer decreases. This further lead to more leakage current and therefore more junction temperature. With the cumulative